A modern AI model can contain hundreds of billions or even trillions of parameters, while using only a small fraction of them to generate each word. At first, that sounds contradictory. Why build a model with an enormous number of parameters if most of them are sitting unused at any given moment? The answer is an architecture called Mixture of Experts, usually shortened to MoE. You'll see this term attached to models from companies like Google, Mistral, DeepSeek, Moonshot, and several other AI labs. It has become one of the main ways researchers make models larger without increasing the computational cost at exactly the same rate. But the name also creates confusion. Are there really separate experts inside the model? Is one expert responsible for mathematics, another for programming, and another for writing? Does the model ask several smaller AIs for advice and then choose the best answer? Not quite. So let's slow this down and build the idea from the beginning. Starting with a normal, dense model. Before explaining mixture of experts, we need to understand what it is replacing. Most language models are built from many repeated transformer layers. Each layer contains different components, but two parts are especially important. The first is the attention mechanism. Attention helps the model examine the tokens in the context and decide which earlier information matters for the current token. The second major component is usually called the feedforward network. That name sounds complicated, but you can think of it as a large transformation applied to every token. Attention gathers information from the context, and then the feedforward network processes that information. In a traditional dense model, every token passes through essentially the same set of parameters in every layer. Suppose the input is, the capital of France is Paris. Each token moves through the model, one layer after another. The token for France passes through the same feedforward network as the token for Paris. A token containing Python code also passes through that same network. So does a Chinese character, a mathematical symbol, or part of a poem. The model can still learn different behaviors for all these inputs, but the same large block of parameters is involved every time. That is why it is called dense. Almost the entire model participates in processing every token. Now imagine increasing the model from 70 billion parameters to 700 billion parameters. If the architecture stays dense, the amount of computation required for every token also rises dramatically. You gain more capacity, but you pay for that capacity every time the model reads or generates something. This creates a scaling problem. Researchers would like a model to contain more knowledge, more patterns, and more specialized capabilities, but they don't necessarily want to activate every part of that model for every word. That is where mixture of experts comes in, replacing one network with many experts. In a mixture of experts transformer, some of the normal feedforward networks are replaced by a collection of smaller feedforward networks. Each of those networks is called an expert. Instead of having one feedforward block in a layer, you might have 8 experts, 64 experts, 256 experts, or even more. But the token does not pass through all of them. A small routing system examines the token and chooses which expert, or small group of experts, should process it. That routing system is often called the router or the gating network. So the basic process looks like this. A token enters the transformer layer. Attention processes the token and its context. The router then gives each available expert a score. The model selects the highest scoring expert or experts. The token is sent only to those selected experts. Their outputs are combined, and the result continues into the next part of the model. That's the central idea. Instead of activating the entire feed-forward capacity, the model activates only the part that appears most useful for that particular token. And this decision can happen separately for every token. The word function inside a programming example might be routed differently from the word function inside a biology explanation. Even 2 neighboring tokens in the same sentence may be sent to completely different experts. The routing can also change from layer to layer. A token might go to expert number 7 in an early layer, expert number 31 in the next MoE layer, and expert number 2 later in the network. So it is not choosing one permanent specialist for the entire response. Routing happens repeatedly as the token moves through the model. A simple numerical example. Let's use an imaginary model to make the efficiency easier to see. Suppose a dense model contains 100 billion parameters, and almost all of them are involved in processing each token. Now imagine a MoE model containing 800 billion total parameters. That sounds 8 times larger. But perhaps the MoE model divides much of that capacity into 16 experts and activates only 2 experts for each token. The full model still contains 800 billion parameters. Those parameters contribute to what the model can learn during training. But the amount of computation used for an individual token might be closer to what you would expect from a much smaller model. These numbers are only an illustration, but the distinction is important. Total parameters describe the complete capacity of the model. Active parameters describe how much of that capacity is used for one token. When you see a MoE model advertised as having 1 trillion parameters, that does not necessarily mean it performs 1 trillion parameters worth of computation on every generated token. This is one reason parameter count comparisons have become increasingly misleading. A 500 billion parameter MoE model may require less computation per token than a much smaller dense model. At the same time, the MoE model may still require far more memory because all those experts have to be stored somewhere. We'll come back to that difference because it's one of the biggest misunderstandings around this architecture. What does the router actually see? The router does not read the token as a human-readable word and say, "This looks like mathematics, so send it to the mathematics department." It receives the token's internal numerical representation. By this stage, the token is not just a word or piece of punctuation. It has been transformed into a vector containing information about the token, its context, and what the previous layers have learned about it. The router applies a relatively small calculation to that vector and produces a score for each expert. Imagine there are 8 experts. The router might calculate scores that roughly look like this. Expert 1, 0.03. Expert 2, 0.07. Expert 3, 0.56. Expert 4, 0.04. Expert 5, 0.21. And lower values for the others. In a top 1 routing system, the token would go only to expert 3. In a top 2 system, it might go to experts 3 and 5. When multiple experts are selected, their outputs are usually weighted using the router scores and then combined. So expert 3 might contribute most of the result, while expert 5 contributes a smaller amount. Top 1 routing is computationally cheaper because only one expert handles each token. Top 2 or top K routing can provide more flexibility and reliability, but it also increases computation and communication. There isn't one routing method used by every model. Different architectures make different trade-offs between quality, stability, speed, and hardware efficiency. Are they really experts? This is where the name can be a little misleading. When people hear expert, they often imagine a clearly organized system. Expert 1 handles mathematics. Expert 2 handles French. Expert 3 handles JavaScript. Expert 4 handles biology. Researchers sometimes do find patterns like this. An expert may activate more frequently for a particular language, type of code, grammatical structure, or category of information. But the specialization is usually not that neat. An expert might respond strongly to punctuation in one context, numerical formatting in another, and a particular sentence structure somewhere else. Some experts may learn broad behaviors used across many subjects. Others may become specialized around internal features that are difficult for humans to name. And in some models, multiple experts appear to learn partially overlapping skills. That overlap is not necessarily wasteful. Redundancy can make the system more robust. If only one expert understood a crucial pattern, the entire model could become overly dependent on that expert. So it is safer to think of experts as separate learned processing pathways rather than a clean list of human job titles. The model discovers how to use those pathways during training. Researchers do not normally assign expert number 17 to Python and expert number 28 to chemistry before training begins. The router and experts learn together. How experts learn during training? During training, the model receives examples and tries to predict the next token. It makes a prediction, measures how wrong that prediction was, and adjusts its parameters. In an MoE model, this includes both the expert networks and the router. If routing a certain kind of token to a particular expert helps reduce the error, the model gradually becomes more likely to make a similar routing decision in the future. Meanwhile, that expert becomes better at processing the kinds of tokens it receives. This creates a feedback loop. The router sends certain patterns to an expert. The expert becomes better at handling those patterns. Because the expert becomes better, the router has more reason to send similar patterns there. That is how specialization can emerge. But this feedback loop also creates a serious problem. What happens if one expert becomes slightly better than the others early in training? The router may start sending more tokens to it. Because it receives more training examples, it improves faster. Then the router sends it even more tokens. Before long, one or two experts may receive most of the traffic, while the remaining experts barely learn anything. This is sometimes described as expert collapse. The model technically contains many experts, but only a few are being used effectively. That defeats the purpose of building the architecture. Keeping the workload balanced. To prevent this, MoE models usually include some kind of load balancing mechanism. The training objective does not only reward the model for predicting the correct token, it can also apply pressure encouraging the router to distribute work more evenly. That does not mean every expert must receive exactly the same tokens. If the model were forced to use all experts equally in every situation, meaningful specialization would become harder. The goal is to avoid extreme imbalance. You want experts to develop different strengths, but you do not want one expert receiving half the traffic while another receives almost nothing. There are several ways to approach this. Some systems use an auxiliary balancing loss. If the router overuses a small group of experts, the model receives an additional penalty during training. Some approaches adjust routing scores to make overloaded experts temporarily less attractive. Others give underused experts a small advantage. More recent architectures have experimented with balancing methods based on the distribution of router scores rather than using only fixed penalties. The exact mathematics varies, but the objective remains similar. Allow specialization without letting the routing system become unstable. This is much more important as the number of experts increases. Choosing 2 experts from 8 options is one thing. Choosing a tiny group from hundreds of experts is far more sensitive. A small change in routing behavior can redirect a large amount of traffic through the system. Expert capacity and crowded experts. There is another practical problem. An expert cannot necessarily process an unlimited number of tokens at the same time. During training or batched inference, the system may be processing thousands of tokens together. If too many of those tokens are routed to the same expert, that expert becomes overcrowded. The hardware assigned to it has more work than the others, and the entire system may have to wait for that one expert to finish. MoE implementations often define an expert capacity, a limit on how many tokens each expert can process within a batch. If an expert exceeds its capacity, the system needs a strategy. Some architectures drop the overflowing tokens from that expert. Some redirect them to another expert. Some increase the available capacity, which reduces token loss but requires more memory and computation. Some use routing designs that try to prevent overload before it happens. This is one reason routing is not simply a classification problem. The router isn't only asking which expert is best for this token, it also has to consider whether that expert has room available and how the decision affects the performance of the whole system. The theoretically best expert may not be the practically best destination when 10,000 other tokens are trying to reach it at the same time. Shared experts. Some MoE models also include shared experts. A shared expert is active for every token, while the routed experts change depending on the input. Why do that? Because not every operation needs specialization. Some forms of language processing may be broadly useful across almost all tokens. Forcing every routed expert to independently relearn the same basic behavior can waste capacity. A shared expert can handle the common foundation. The routed experts can then focus more of their capacity on features that benefit from specialization. You can think of it as a company with a central administration team and several specialized departments. Every project uses the central services, but only selected departments handle the specialized work. Again, the analogy is not exact, but it captures the reason shared experts can help. They provide a reliable general pathway while sparse experts add conditional capacity. Why MoE can scale efficiently? Now we can answer the main question. Why use this architecture? Because it separates model capacity from computation per token. A dense model ties those two things closely together. Adding more feedforward parameters means using more feedforward parameters for every token. An MoE model can add more experts, increasing the total number of parameters without activating every new expert each time. This gives researchers room to train models with much greater total capacity while keeping the active computation more manageable. More total parameters can help the model store more patterns and develop a wider range of internal behaviors. But because only a subset is activated, the cost of generating each token does not increase in direct proportion to the total size. That doesn't make scaling free. Training a huge MoE model still requires enormous hardware, data, and engineering work. But it creates a better scaling curve than simply making every layer dense and larger. This is why mixture of experts has become so attractive at the frontier. The architecture allows labs to build models that are enormous in total capacity without making every token impossibly expensive. The memory problem? Here's the catch. Sparse activation reduces computation, but it does not automatically reduce the amount of memory needed to store the model. Suppose the model has 500 billion total parameters, but only 50 billion active parameters per token. The hardware may perform something closer to 50 billion parameters worth of expert computation for that token. But the full 500 billion parameters still need to be available when the router decides which experts to use. You cannot store only the currently active expert unless you already know what future tokens will require. In practice, experts may be distributed across multiple GPUs or even multiple machines. This is why an MoE model can be relatively efficient to compute while still being extremely difficult to run locally. People sometimes look only at the active parameter count and say, this model activates only 20 billion parameters, so it should run like a normal 20 billion parameter model. That leaves out the storage problem. Unless you use aggressive offloading, all or most of the expert weights still need to fit somewhere. Offloading experts from normal system memory or storage is possible, but moving those weights repeatedly can make generation extremely slow. So MoE gives you sparse computation, not magically sparse storage. What happens across multiple GPUs? Large MoE models are often spread across many GPUs using something called expert parallelism. Different GPUs store different experts. Now imagine a batch containing thousands of tokens. The router examines each token and decides where it should go. Some tokens may need experts stored on GPU 1. Others may need experts on GPU 7. Others may need experts on GPU 25. The system groups the tokens by destination and sends them across the GPU network. Each GPU processes the tokens assigned to its local experts. Then the resulting activations have to travel back so the model can continue through the next layer. This often involves a communication pattern called all-to-all communication. Every participating device may need to send data to several other devices and receive data from them in return. And that can become expensive. Modern GPUs can perform calculations extremely quickly, but if they spend too much time waiting for data to move across the network, some of that computing power sits idle. This means an MoE model's performance depends not only on the GPUs, but also on the connections between them. How much bandwidth is available? How much latency does each transfer add? Are the experts distributed efficiently? Are the tokens balanced across the devices? Can communication happen at the same time as computation? These infrastructure details can determine whether a theoretically efficient model is actually fast in production. Kimi K3 as an extreme example. The Kimi K3 architecture from your previous video is a useful example of how far this design can be pushed. According to the supplied material, Kimi K3 contains 896 routed experts and selects only 16 of them for each token, alongside shared experts. That means only a small percentage of the expert pool is activated at a time. But selecting 16 experts from a pool of 896 also creates a serious routing and communication challenge. Those experts may be spread across a large group of GPUs. Every token could potentially need data from experts located on different chips. Moonshot's reported approach includes something called stable latent MoE. Before routing the token representation across the expert system, the architecture compresses it into a smaller latent representation. The smaller representation requires less data to be transferred between GPUs. After the selected experts process it, the result can be projected back into the model's full internal dimension. The basic idea is similar to compressing a large document before sending it over a network. You still transmit the useful information, but you reduce the amount of traffic. This illustrates how modern MoE research is moving beyond simply adding more experts. The difficult part is no longer just deciding which experts to activate. Researchers also have to ask how the experts communicate, how routing stays balanced, and how the entire architecture fits the physical hardware. At this scale, model design and data center design begin to overlap. Why sparse does not always mean faster. You might expect an MoE model with 10% of its parameters active to run 10 times faster than a similarly sized, dense model. Usually, it doesn't work that cleanly. First, the attention layers may still be dense. MoE commonly replaces feedforward sections, not necessarily every part of the transformer. Second, the router itself adds work. Its cost is relatively small compared with the experts, but it is not zero. Third, dispatching tokens and combining expert outputs creates overhead. Fourth, communication across GPUs may become a bottleneck. Fifth, each expert receives only part of the batch. Modern GPUs work most efficiently when they process large, well-organized blocks of data. If traffic is divided across many experts, each expert may receive a small or irregular workload. And sixth, generating text is still sequential. The model generates one token, then uses that token to generate the next one. Even if the internal computation becomes more efficient, other parts of the generation process still limit speed. So MoE often provides better compute efficiency for a given total model capacity, but that is not the same thing as saying it will always have lower latency. A dense model can sometimes be faster for a single user or a small batch because it has a simpler and more predictable execution path. MoE becomes especially attractive at large scale, where providers can batch many requests together and keep the experts busy. Training is not automatically cheap. There is another common misunderstanding. If only a small part of the model is active, training an MoE model must be cheap. Training may be more compute efficient than training a dense model with the same total parameter count. But these models are still extremely expensive to build. All experts need to learn. The training system needs to store their weights, gradients, and optimization data. The router needs to be trained. Tokens need to be moved across hardware. Load balancing has to be monitored. Failures in routing can waste large training runs. And because the goal is often to build a model with far more total capacity, researchers may use the efficiency advantage to make the model much larger rather than to make the project inexpensive. It's similar to improving the fuel efficiency of an aircraft and then using the improvement to build a much larger aircraft. The larger aircraft may be efficient relative to what it can carry, but operating it is still not cheap. Fine-tuning and MoE model. Fine-tuning also becomes more complicated. With a dense model, Every training example updates the same general set of feedforward parameters. In an MoE model, examples may be routed through only a subset of experts. Suppose you fine-tune the model on medical text. Does the training improve all experts? Probably not equally. The router may send most medical examples to a particular group of experts. Those experts receive more updates, while others change very little. That may be exactly what you want. But it can also produce routing shifts, imbalance, or overspecialization. Fine-tuning the router too aggressively may cause the model to forget how to distribute general traffic. Freezing the router may preserve stability, but prevent the model from discovering a better expert arrangement for the new domain. Parameter-efficient methods such as adapters can help, but the sparse architecture still introduces extra decisions. Where should the adaptation be added? To every expert? Only the experts that receive the target data? To the router? To shared components? There is no single answer that works for every model and task. Common misconceptions. Let's clear up a few misconceptions. First, mixture of experts is not the same thing as an AI agent system. An agent system may use several complete models or several copies of a model, each performing separate tasks. Inside an MoE model, the experts are components of one neural network. They are not independently writing answers and debating with each other. Second, the model does not normally route the entire prompt to one expert. Routing usually happens token by token and layer by layer. Third, experts are not guaranteed to correspond to recognizable human subjects. Some may show understandable specialization, but others learn abstract internal features. Fourth, total parameters and active parameters are not interchangeable. Total parameters affect model capacity and storage. Active parameters more directly affect computation per token. And fifth, an MoE model is not automatically better than a dense model. Architecture is only one part of model quality. Training data, optimization, attention design, post-training, reasoning methods, and tool use can matter just as much. A poorly trained trillion-parameter MoE model can still perform worse than a carefully trained smaller, dense model. When dense models still make sense. With all these advantages, why not make every model an MoE model? Because dense models remain simpler. They are easier to distribute across consumer hardware. Their computation is more regular. They avoid routing instability. They do not require all-to-all expert communication. Their latency is easier to predict. And every parameter receives training signals from every relevant token passing through the layer. For smaller models, local models, and situations where memory is limited, dense architectures can be extremely competitive. A dense 8 billion parameter model can be loaded onto one GPU and process every token through a straightforward pipeline. An MoE model with the same active parameter count might contain 40, 80, or 100 billion total parameters. It could require much more memory and create more complicated hardware demands. So the choice depends on the goal. If you need maximum total capacity at data center scale, MoE can be very attractive. If you need a model that runs efficiently on one device, a dense model may be more practical. What MoE changes about the AI industry? Mixture of experts also changes how we should think about model scaling. For years, people compared models using one simple number, parameter count. A 70 billion parameter model sounded more capable than a 7 billion parameter model. But with sparse architectures, that number tells only part of the story. Now we need to ask several questions. How many total parameters does the model contain? How many are active for each token? How many experts are available? How many experts are selected? Are there shared experts? How much of the architecture remains dense? What hardware is required to keep the full model in memory? How much communication is needed between devices? And how efficiently is the model being served? Two models can have similar total parameter counts and very different computational costs. Two models can have similar active parameter counts and very different memory requirements. And the same MoE model can perform very differently, depending on how well a provider implements the routing and expert communication. This makes infrastructure a bigger part of model performance. The weights alone do not tell you the whole story. Where the architecture may go next. Researchers are now working on several parts of the MoE problem at the same time. Some are increasing the number of experts while making activation even more sparse. Some are designing better load balancing systems that do not require large auxiliary penalties. Some are adding shared experts for common knowledge. Some are compressing the information sent between devices. Some are experimenting with expert choices at different levels, not only token-level routing, but routing entire sequences, tasks, or groups of tokens. Others are trying to make experts more hardware-aware. Instead of choosing only the mathematically best expert, the router may also consider where that expert is located and how expensive it is to reach. That could reduce communication without sacrificing much quality. We may also see more models that combine MoE with other efficiency techniques: quantization, compressed attention, recurrent memory, speculative decoding, and smarter caching. The larger point is that future model progress may depend less on simply adding more computation and more on deciding where computation is actually needed. A dense model treats every token as if it deserves access to the entire network. A mixture of experts model says something more selective. This token only needs a few parts of the network right now. Let's identify those parts and use them. Closing. So, mixture of experts is not a collection of little chatbots inside a larger chatbot. It is one neural network with many possible processing pathways. A router examines each token. It selects a small number of expert networks. Those experts process the token. Their outputs are combined. And the model repeats that process across many layers. The advantage is conditional computation. The model can contain far more total capacity than it activates at once. The cost is complexity. Experts have to remain balanced. Tokens have to be routed reliably. The full model still needs enormous memory. And when experts are spread across multiple GPUs, moving information between them can become just as important as the calculations themselves. That is why mixture of experts is both elegant and difficult. On paper, it sounds simple. Build many experts and use only the ones you need. In practice, the hardest part is making hundreds of experts behave like one coherent model. And as models continue growing, that ability to decide which small part of a massive network should work on each token may become just as important as making the network larger in the first place.